Hello everyone, I am Shiv Prakash, Research Scholar, Department of Electrical Engineering, IIT BHU. I am here to take your assignment session for the course control and tuning methods in switch mode power converter. This subject being taught by Professor Shantanu Kapur sir, Department of Electrical Engineering, IIT Kharagpur. Okay, some wait for the student joining the session. Assignment 2 session will next Tuesday. So wait for next Tuesday. This time, same time, I will solve all assignment question in the next Tuesday. I think some technical error here are presenting. Okay, wait. Here the first question. Wide band gap devices have junction temperature, conduction losses, and switching losses. I think wide band gap, such type of some type of devices where the balance band and connection band gap is higher than the silicon devices, other normal devices. That's why you used wide band gap devices for the higher blocking voltage. Reverse blocking voltage is higher of the wide band gap devices, like germanium. You know germanium 0.67 electron volt energy. The balance band here, and here the conduction band. The gap between the balance band and conduction band in large with respect to the silicon devices. That's why the junction temperature, I think, will take a high temperature to conduct, and conduction losses is low because of the input, because of the resistance, on resistance of that devices is very low, and switching losses also low for the wide band gap, but costly I think is silicon carbide and gallium nitride. This one is the wideband gap devices. This energy gap 3.3 electron volt for silicon carbide and gallium nitride for 3.4 electron volt. More than that, this is an insulator of energy. Okay. This one second question. For the circuit given below, derive the efficiency of the circuit. This question is not for assignment session, but I have taken this question because of some student doubts for deriving the efficiency of that circuit. So let's start. V naught. First we written the KVL, simple KVL for V naught. The V in minus Is into Rs. Because of this voltage is same as this voltage V naught. V in minus Is Rs and also known as Is is equal to Ic plus I naught from the circuit. Here in the circuit we can replace the Is from Ic plus I naught. Then we find I naught Rs. That's why V in minus Is Rs. Unless you can also replace I naught here like a V naught by R into Rs. Take a V in common there, and V naught is equal to V in 1 minus Ic Rs. V in first to find the gain, voltage gain V naught by V in, like that 1 minus divided by V in here take V output V in common, from that we find 1 plus Rs by R equal to 1 minus Ic into Rs divided by V in. You know the voltage gain V naught by V in is equal to sorry, is this plus voltage gain? I think here is the plus from the output of V in. Yeah. That's why we also taken R minus Ic into R like given questions. You know about the V efficiency. Efficiency means output power divided by input power. Output V output into I naught divided by V in into Is, and you also find the voltage gain, and next you find the current I naught by Is. For this you applied the KVL in the input voltage side, like this loop. Then you find I naught. V equal to Is into Rs plus I naught into R. You also know the I equal to Ic plus I naught. You replace it, Ic plus I naught into Rs plus I naught into R. Screen some problem occurs yet. Wait for some time. Yes, screen is not right. Okay, I solve this. Wait some time. Yes. Wait. Yes. Now it's okay. I think this Is, sorry. And this IC is considered. Okay. I shift here. Now I see into R. Display delay efficiency no V voltage gain चलती कभी find it and I naught is equal to V in minus IC into RS divided by R plus RS and what be IS find here IC into R. Okay, here R plus RS cancel out in both denominator, then efficiency you find if you take a V in common then find efficiency like the present in the questions. This one. Okay, go for the third question. Third question is which of the following is a characteristic of the linear dropout regulator? Actually, this linear dropout regulator is used for the IC, given the power to the IC. It is used in the low power application because of actually you know microcontroller IC needed up 3.3 volt or less than 3.3 volt. Also some ICs are 5 volt. This that's the reason you use the LDO because of this is the low power application and this output voltage is a constant voltage. If you use the you know about the buck converter, boost converter, like that if you use a buck converter then the output voltage some having some ripple voltage. That's why we use the linear dropout regulator. Here the voltage divider is used. That's why you use only the step down voltage application. Step down like a 5 volt to 3.3 volt or 3.3 volt to 1.2 volt like that. So the efficiency is very high. Then first option is not correct. And used very low power application. I think ICIC take a milliampere in current and voltage is 3.3 volt. This one is the second option. And step up operation is also not possible because the voltage divider is used. EMI is not affected because of the not present in the present of inductor. If inductor you use the EMI is more that circuit like boost converter. Okay. Buck converter used that's why is not suffer from the EMI and use the ultra low power application. Then first question is the primary causes for not operating a conventional boost converter at no load. Okay, first the boost converter. So inductor and here given the no load. No load means disconnect the resistance from the output terminal. circuit is like behave like a open circuit output side, but capacitor present here. When you start switch on, that time inductor will charge at DTA cycle in the time on period, and 1 minus D is the turn off period. Inductor will charge, then when the charge the switch is off, then reflect energy to the capacitor. Capacitor will charge. Once the capacitor will charge, after that this is fully charged. But there is no path to discharge own energy because of resistance also not present, and the diode also in the reverse bias condition. That's why capacitor will not discharge. If capacitor not discharge, then it violate the capacitor charge balance. Because if you use any circuit, capacitor used in any circuit, the must have the discharge and charge and discharge the capacitor and inductor. Inductor will discharge first time, but capacitor will not discharge. It is fully charged once. And if you the if you use a second cycle, go for the turn on the switches. That time you feel like a huge voltage on the switches, and switches. Okay. Switches will burn out also because of the inductor current will not flow through the capacitor because of capacitor fully charged. So that the opens when the switch on, the capacitor will charge, but okay. Inductor will charge, but it will not discharge through anywhere. That's why the huge voltage appears in the devices, and used as like a MOSFET, and MOSFET may be burn out. That's why it is not used at a no load. Boost converter not operated at no load condition because of the violate the capacitor charge balance. Yes. Questions. For an ideal boost converter, the average load current and the average input current are given to be 6 ampere and 10 ampere respectively. The average value of switch current will be the first boost converter. V naught here. Some error occurs. Okay. Some given 6 upon 1 minus 2. So you find D is equal to 0.4 to ratio. You know switch current. Switch current will flow when the switch is on. When the switch is on, then current will flow, and the switch is off, then current will not flow through the switch. That means the input current flow when switch is on in the circuit. That's why you like a switch current is equal to due into input current, like a 4 ampere. The screen I think stopped. Okay, wait. So number 6 is equal to will like voltage divider use here for the V1 and 1 by SC1 plus 1 by SC2 minus C1 cancel out and VC2 upon SC1 plus C2 same as will like and V1 V is equal to I think 16 volt V, yes, and C2 is equal to 3 microfarad and C2 C1 is equal to 5 microfarad and here 3 by 8 3 microfarad and 8 microfarad cancel out and you find V1 is equal to 6 volt. And similarly you take the V2 is equal to 10 volt. After that question number 7, initially yes was on and the circuit was made to reach its steady state. The current IR at 2 microsecond. Okay, Next, draw the circuit for the switch S bar is on, and C1 S is open circuit and S2 is closed. S1 is closed. So that this loop only present here in the final circuit. Let's draw the circuit. So C1 open circuit. This one is V2. Okay. Let's check. Overall is on, then S was off. Yes. Switch S is on and S bar is off in question number 6, I think. Yes. Connected. S bar is off. Okay, fine. Next, you know about the current formula in the circuit, the discharge circuit, I think, what is present. Is equal to V naught V by R, so e to the power minus T by tau, where tau is equal to RC. RC means resistance and capacitor equivalent, but here there only one capacitor present in the full circuit, so we use the 3 micro 3 microfarad equal to 30 microsecond. Oh, this microsecond. So T is equal to 2 microsecond. This will be here. Is equal to 10 V by R, 10 by resistance is also 10 here. E to the power minus 2 into 10 to the power minus 6 divided by 30 into 10 to the power minus 6. 10 cancel out, 10 to the power minus 6 cancel out, minus 1 by 15. And if you solve this, you find is equal to approximately 0.935. Okay. Question number 8. Converter shown in the figure is ideal and the inductor current is continuous conduction when operating in the steady state. V is equal to 20 volt and V out is equal to minus 5 volt. And duty ratio of the switch. Here you see the circuit is a buck boost converter. You know about the buck boost converter. Output is here negative and here positive. No formula. V naught is equal to minus dV in by 1 minus d, because of the polarity is reverse here. In conventional, you know this is positive terminal, this one negative terminal, but in the question this is opposite of the sign. I think this one plus, this one minus, so that you put a minus here. V naught is equal to minus dV in upon 1 minus d, so that you will take V naught is equal to minus 5, 1 minus d, 1 minus d is equal to 4d, and d is equal to 1 by 5 equal to 0.2 duty ratio of the converter. This question number 8. Question number 8, you see, then if you observe the question number 8, you find its behavior like a buck boost converter. uh, okay, someone help me. First, where the Q is present means duty ratio. He has the Vx. Vx is between the switches, voltage across the switches. Yeah, I think R3 is the internal resistance of the switches. Collecting series resistance. Oof. The screen or something. Wait. Yes. He asked Vx is between the these are the voltage across the switch. Yes. Uh, you observe the circuit, you find a switch where the switch Q that one is this one, second, third is fourth switch. So when first or second switches is on first time in the Q cycle, you know that, then this one circuit is like that loop, behave like that loop. Is present only R1, inductor RL and R3. All of I remove the entire circuit. This one, and when the switch is off, this one present in the 3 or 4 around. Then this cycle loop is flowing in the circuit. That's why you see the behavior of this converter in the like a buck boost converter. As of know about the buck boost converter, here I draw the circuit or the boost converter. Yeah. Should I this is V in the output, and the charge current this time and this time discharge, like this circuit. If you observe this, this will behave like a buck boost converter also, because when the one or second first or second is on, then the inductor will charge, after that it will discharge. Okay, I draw the circuit when the first second is on and remove the all of circuit. Why you not consider the cross R1 and RL? Okay. I think voltage you asked asked voltage across the switches across the R3. That's why I take only R3. First I draw the circuit, after that I explain it. When first second is on, switch on, all RL, this one R3, this one switch on. Okay. This one L, R3, this one IL. this voltage across Vx is this voltage we asked. That's why I take a loop of that, then you find Vx, then you equal to IL into R3. Vx is equal to, you find here, because of current flow IL, same current flow in the R3, and voltage drop across Vx is only R3 resistance is present. That's why you take a Vx is equal to IL into R3 circuit. Term of V in option C is also correct. Why we have not considered voltage drop in RL, R1 and RL. Okay, I think it used to be minus IL into R1 plus RL. Yes, I think Vx is equal to V in minus RL IL voltage drop. Actually, inductor also present here. You can't neglect this. Some voltage drop also occurs here in the loop. Observe, then you find some voltage also occurs at the circuit in the inductor voltage drop, but a voltage across the inductor is not given. That's why you can't take this loop. So Vx is equal to only IL into R3 is higher. If IL is given, then you can apply this loop also. We can send the voltage of R3 the same one. Yes. Only observe the switch voltage only. The second and the third and fourth switch is on. First time I'd rather draw the circuit and remove all of part. You find like only R2, L and R4 I think, and this one capacitor C. Some RSC I think. It's okay. This is V0 and voltage asked Vx is like this node. If you apply KVL in this loop, then you find the Vx value. There is some, but you don't take a whole of circuit. You take only Vx, R4 and RC also. This IL current flow across the R4 and RC. That's why you find only for that. Vx is equal to IL R4 plus V0. First option is correct. When first and second switch is on, then ILR3 will find, and when the switch of third and fourth will on, then ILR4 and plus V0 will find. Okay. Okay, next question. I think screen stop. Wait. Yeah. Consider the following circuit. Here RC parallel circuit connected in series with the R3. If you observe this, you know about the battery model. You know about the battery model. The circuit show like a battery model, where RC parallel circuit present and R3 is like internal resistance of the battery, and B in is constant voltage. If you model any battery, that you find this type of circuit. Your circuit is say about the model of this. If you estimate SOC of the battery, that's why this circuit also take. Okay, I convert in the Laplace domain of capacitor and a circuit. So R1 one wise, yes. Minus V0, this one V S1, S2, R2, R1, this one IN, R3. You solve this parallel circuit, you find the equivalent impedance. IN, you find R1 upon 1 plus SC1 R1. Same as here, R2 is equal divided by 1 plus CS C2 R2. Here R3 is alone. Apply KPL in the circuit. For output of voltage, you need the voltage in form of input voltage and input current. V in minus I in, and impedance, first impedance plus second impedance plus R3. You find V in minus I in, you take R1 common, and you find like this is the 1 plus SC1 R1 and 1 plus SC2 R2 is the feedback closed loop system. solve that. 1 plus AB like that. One common so divide 1 minus into R1. If you take the negative feedback system, that's why I take the negative minus AB like that. And in into R2, second common of R2. You rearrange this G upon 1 minus GS like that, 1 plus GS in the closed loop system like for negative feedback system. Minus I into R3. And second I take place here the circuit whole circuit. Sorry is negative. I think B option is not this. Not a negative feedback. B option is then positive feedback. That's why you can't take this option. First is wrong because of the feedback system. You would apply this. You can't find that. B and C is the same, but feedback is the positive feedback here. So I did this B option not correct. And in the C option, you find the negative feedback system and you apply the loop between the inner loop out this loop, then you find the same equation where you present this B in okay R1 here multiply and R2 also. That's this option is correct. Okay, all of some questions here. I think. So question reason I have asked that two questions for the same reason. To the similar question about the email discussion from all the course. That why we only consider R3. Okay, but here you can't take only you can't take a R1 like that because of this inductor present here. That's why. If inductor is not present, then you can take this. Which is a good book, textbook. I think you take a Rexon writer. I think book present you find in the power inductor converter. So question number 1 second. What is first second? Okay, I'll take option name Rexon. I will just do for you. And the first question: the wide band gap device says have junction temperature. Okay, so the wide band gap devices, the Fermi layer energy will very high to work as a work as a conduction. That's why junction temperature high. It means they use the high temperature. If you give, then wide band gap devices will conduct, and other devices will conduct at low temperature also. This is the property advantage of that. You can operate at a high temperature also. These devices like silicon carbide and gallium nitride. You observe that this one is a higher energy you need to break the bond of the element of the atom. Question number second. Question number second is a simple like voltage KVL loop. First you used output voltage loop. You see it like a V in minus Is into Rs. Second one, you take input side voltage. That's you find the efficiency. First you take output voltage, after that input voltage, then find the voltage gain. You know like kV constant given. After that you find the efficiency, voltage gain and current gain. In V in you find the I naught and Is. You find I naught and Is, then you find the efficiency. Okay, I think I have a question. Thank you to everyone. The assignment second will the session will at next Tuesday same timing. You can meet. Okay, thank you.